turned you loose and you did a little bit of work, right? So we were trying to come up with the equation of a line, of a tangent line to a curve at x equals 2. Now let's work backwards on this. If I want to come up with the equation of a line, what are the ingredients of the equation of a line? What do I need? A point and a slope, right? Exactly, I need a point and a slope. The point is algebra 1 stuff. That's a piece of cake. If I know the x coordinate, how do I find the y coordinate of the point? Plug it in. Absolutely. I just plug this in for x, and I get f of 2 equals 6 minus 3 is 3, right? So I get the point 2, 3, and I think we came up with that yesterday somewhere at the top. Right there. Yep, there's my point. Okay, the slope is the calculus part. That's the tricky part. How do I come up with the slope of a function? Whose job is that in calculus to calculate slopes? What function gives us back the slope, the value of the slope? The derivative. That's the job of the derivative function, is to calculate slopes, right? That's what it does. The derivative function is the function that gives me the slope of the curve for any input value of x I choose. So that was the one that required a little bit of work, right? Now what do we do? Well, we always start off with our template. That's our template right there. That's the definition of a derivative every time. Then we just have to get specific based on what problem we're doing, right? What is our f of x, for example? Our f of x is x squared plus x minus 3. So we had to make our, if that's f of x, then we had to replace f of x plus h with what we get for our function. We had to replace f of x with our function, and we had to do our limit magic, right? Where we take this indeterminate form. If I try to evaluate this directly, it just looks like 0 over 0. So I've got to expand everything out, and what we found is all the terms without h's canceled. We call those the naked terms. The terms with no x's or no h's, all are going to cancel. So everything that's left over has a factor of h, all the terms. So I can factor an h out and cancel, and then that's what's removing the indeterminacy. Because we did this, a few weeks ago. You guys would have told me from the beginning, when this is indeterminate, what's the factor that has to cancel? Well, it's going to be h over h, right? Because when h approaches 0, what factor is going to turn into 0? Well, h, right? The factor h is the factor whose 0 is 0, right? So we knew ultimately I was going to have to be able to cancel h's on the top and the bottom, and then this is how we did it. We factored out an h, we canceled them, and then I was left with an expression that I could evaluate directly, right? I could plug in h equals 0, and it was no longer indeterminate. Two of the terms didn't even have h's in them anymore, right? So those were done. This other term did have an h, and when h went to 0, that term disappeared. And I just ended up with 2x plus 1. So that was my derivative function. Now to find the slope of the tangent at x equals 2, I just plug 2 into my derivative. And that gives me the slope of the tangent line. Well, now I've got my ingredients. If I've got the slope of the tangent line, if m equals 5, and the point has coordinates 2, 3, really, this is just algebra 1 now. I'm going to use point slope, right? So what is point slope? Times the quantity x minus x1. So when I plug in, what do I get? Good. And if on the AP test, for example, you would just leave it like that. You don't even have to even do anything. That's the equation of the line. You really, I mean, simplifying that isn't hard to do. I think on your assignments, you're going to have to write that in slope-intercept form, but what are the last two steps always going to be? Distribute and then move that term, right? Remember, putting a linear equation into slope-intercept form literally just means isolating y and simplifying. That's all it is, right? So if we distribute, we get 5x minus 10, add 3. Don't I just get y equals 5x minus 7? And that's it. Okay? Well, let's look at that. See what we just did. That's kind of cool. What did we accomplish? Oh, I don't have a graph. Well, let's graph it. Okay, so let's graph this function, f of x equals x squared plus x minus 3. There it is. Okay. What we're trying to do is find the slope of the tangent line at the point x where x equals 2, right? Now, I want to show you some really cool tricks in Desmos. You guys should be messing around with Desmos, because one of the fringe benefits of a class like this is you should emerge just being experts at Desmos, because it is a really valuable tool. Well, one thing you can do is we can set up an ordered pair here. 2, and then I don't even have to calculate the output of f of x. I can just do, from my y coordinate, I can just do f of 2. Look what it does. That's pretty cool. So what would I call that point? If that's the point where I'm trying to calculate the slope of the tangent line. That's the point of what then? True, but it's a specific intersection, right? We're trying to calculate a tangent line, so that's what we'd call the point of tangency. Okay, what's that mean? If I talk about the point of tangency, it means the point at which the tangent line intersects the curve, grazes the curve. But it's a specific kind of intersection. It's not just a cutting through, it's a tangency intersection, right, where it approximates the slope of the curve. And we said what that was. Like, I can graph the function. Didn't we just say it was y equals, what was it, 5 minus 7? Hey, what do you know? How about that? That is pretty clearly the answer, isn't it? Right? That's the tangent line. Okay. I could have gotten that a different way too. Look what I can do in Desmos here. I could do something like, I can say g of x equals, how cool is this? F prime of x. And that gives me the graph of the derivative function. Okay? Well, first of all, does that make sense that that purple graph is the graph of the derivative? Now, those of you who, what day was it? Was that last Thursday that I did that? We did it in class because a bunch of people were gone. Right? Was that the day that we looked at those graphs, kinematics graphs, and we started with a position graph and we sketched the graph of the derivative and then the derivative of the derivative, right? I gave you position and you guys calculated velocity, which is the derivative of position, and then you took that graph and you calculated acceleration, which is the derivative of velocity, right? So if you missed that day, you want to go back and watch that video. It's not super long, but you definitely want to go back and watch that video. Let's hit an example here that'll kind of reinforce that, and if you haven't seen that yet, let's talk about why that makes sense. Why does it make sense that the purple line is the graph of the derivative of the red curve? Okay. Okay, but that wouldn't even have to happen necessarily. That's just accidental, right? But fill in the blank for me here. The value of the derivative equals what relative to the curve? What is the job of the derivative again? To calculate slope, exactly, instantaneous rate of change. So it's the slope of the curve, right? And here, I tell you what, let's build another Desmos. Let's build another one here that does something different. So we know what g of x is, right? G of x is our derivative function. Let's turn that off. And yeah, let's do something a little different here. Okay. I'm going to choose a parameter a. We're going to let a be whatever we want to. In this case, we're going to let a equal 2, but it could be anything, right? So f of 2 ends up being 3. Do you see what I just did there when you built? Have you guys done this stuff in Desmos? Yeah. What's your familiarity with Desmos? 1 to 5. 5 meaning you are an expert, 1 meaning I have barely ever used Desmos. Okay. 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 So we all want to get to 5s by the end of the year. So that'll happen naturally. But when you do something like this, like if I define some function with x's, and then I come down and I evaluate that function with some different symbol like an a, and typically what you want to do in Desmos, like a lot of times we use t's in physics, which is fine. I could have made this f of t, but it's always a little bit easier to use x as your input variable, to just make that transition, that substitution. Because Desmos is naturally equipped in the xy plane to let x be the input. That's just more convenient for some really subtle reasons I don't want to talk about right now, but eventually I'll point them out to you. Just in general, that's helpful to do. When I plug in something like f of a, it's automatically going to ask you, okay, that's a parameter. It's going to ask you, do you want to create a slider? And you're going to say yes, because then you can come down here and you can plug in any value you want for a for that parameter, and this function is going to treat that like a is some constant value that you're choosing, right? In this case, a is the value that we're choosing for x. So we're just choosing a specific value of a variable, something like x sub 1 or x sub 2 or something, right? Okay, so then it calculated the output, which was 3. Now what we want to do here is we want to be totally general, because I want to be able to flip the value that I'm choosing for my input, and I want to come up with a point of tangency. Well, the point of tangency would just be, what's my x coordinate going to be? A. And what's the y coordinate going to be? F of a, exactly. And then I can pick any value I want for a, and look what that point's going to do. It's going to react. Okay, that's pretty cool, right? That we can do that. And then I can just set that to be 2. There it is. Okay, I want to use that as my point of tangency. Well, look what we did. We already defined the function g of x as the derivative of f of x. So I have a point whose coordinates are a and f of a. In order to come up with the equation of a tangent line, I just need the slope of the function at x equals a. How would I find that? F prime of a. Or I could even just call it g of a, because g is defined as f prime. Everybody see that? Okay. So now if I wanted to come down here and I wanted to come up with the equation of a tangent line, I don't even have to be fancy and write this in slope-intercept form. I can just write it in the form of a linear equation. It doesn't have to be simplified. So I could just leave it in point-slope form, right? So what is point-slope form? Y minus, what was it again? Right, y1, which is going to be f of a, isn't it? Everybody see that? So y minus f of a equals m. Well, what's m? F prime of a, right, in this case, or g, whatever you want to call it. We'll just call it f prime. F prime of a, I could have called it g of a, times what? X minus a. Hey, look at that. Look what we got. I got the equation of the tangent line, but look how cool this is. Isn't that amazing? So that green line is always going to produce the equation of the tangent line because that's what we told Desmos to do, right? Based on whatever value of a we happen to have slid to, it's going to calculate the equation of the line at that specific value of a. Isn't that cool that you can do that? And look what it does, right? The value of the slope of the function is the slope that we're using to define that line. Okay? Everybody see that? Okay, now watch what happens if I graph the function g of x. Okay? Let's also, while we're at it, let's create the point a comma g of a. Okay, so now this is getting kind of messy. But look what happens here. As I slide this value of a, notice that the slope of the function, which is the output of which curve, what color? Purple. Right? The purple graph is the graph of the derivative function. Okay? Well, notice what happens when we let a equal, let's see, where's the vertex of this red graph? It occurs at negative 0.5. Okay, well, let's let a equal negative 0.5. Hey, what do you know? The value of the derivative is 0 there. That makes sense because what's the slope of the tangent to the curve at the vertex of that parabola? Well, there's the tangent line, the green line. What's the slope of that green line? 0. It's horizontal, right? So that makes sense, doesn't it? The place where the red graph has a horizontal tangent line, a tangent line with a slope of 0, must be the place where the purple derivative function has a value of 0. So now listen to this statement very carefully. The value of the derivative function equals the slope of the function, right? Isn't that the job of the derivative function? To calculate a slope, right? So if we're traveling along, if an ant's walking along this red parabola, he's at the bottom of the valley where the slope is 0. If I roll a ball inside this valley, it's going to come to rest there, right? Because that's where the slope is 0. If he walks to the right from there, what's happening to his slope as he walks to the right? It's getting increasingly positive, isn't it? It's increasing. Well, that makes sense. Look at the value of the purple function. It's moving from 0 to greater and greater positive values. Makes sense, right? If he were to walk backwards to the left, he would be reaching greater and greater negative slopes, steeper and steeper negative slopes. Look at the purple function. It's getting more and more negative valued. Okay, give me 1 to 5 on that. Do you see in that connection there? You're right. The green line's just there as a visual aid, just to show you that it's a tangent is all, right? Okay. And maybe, here, I'll tell you what we could do that would make this even better. How about if I make that green line dashed? Right, so now you can see it's something different. It's just there as a visual aid, right? And so look at that. As we climb up into positive values of the derivative function, the slope gets steeper in the positive direction. Bigger and bigger negative values of the purple derivative function indicate steeper negative tangent lines, negatively sloped tangent lines. Make sense? Okay, now we could be really tricky. What if we wanted to calculate the derivative of the purple function, which we're going to come to call very soon the second derivative of the original function. The second derivative is just the derivative of the derivative. What would the third derivative be? Exactly. There you go. Well, it's a big purpose, because if this red function were a position function, the purple function would be a velocity function, and the new function, which we'll make blue, would be what? What's the derivative of velocity? Acceleration function, exactly. So let's do that. Let's calculate the derivative of the derivative. Okay, so we're going to call this one h of x. So we'll call this h of x. Oh, how come it's not? Oh, cancel. I had something else going on there. There we go. H. You can. Yeah, you can make all kinds of cool pictures. So h of x equals, why does it keep doing this? Okay, leave, that's fine. H of x equals, and I could either say g prime of x, or I wonder if it does, I don't even know if it does this, I can't remember. F prime prime of x, yeah, it does it. How about that? So that's why you say second derivative, it's double prime. And let's make this one, we'll make it orange. There we go, it's orange. So there's my derivative function. Well, doesn't that make sense? Because what can you tell me about the slope of the purple function? I mean, what can you tell me about the slope of that purple function? It's constant and positive, isn't it? Because it's a line with a positive slope, right? The slope was, I think it was 5, wasn't it? So, no, it wasn't. It was, must have been 2. If we go back to our problem, the derivative, right?
Wait, so the slope of the first derivative is always equal to the y-intercept of the second derivative?
Okay, no. The slope of the first derivative is given by the derivative of the first derivative, which is the second derivative. Okay, right? Well, we actually don't. I mean, we would, if we were doing this derivative, right, if we were actually calculating the derivative, we would have to know, we'd have to find out what is the first derivative function, and then take the derivative of that first derivative function to get the second derivative function. It just looks like f double prime. Yeah, f double prime is the second derivative. Okay, but this makes sense because the purple graph is the graph of the derivative of the red curve, right? Okay, the orange graph is the graph of the derivative of the purple function, right? So it's just, the orange function is just doing to the purple function what the purple function did to the red function, right? We're just transferring that relationship, right? You get that? So this makes sense, right? Because no matter where you step on the purple graph, the derivative, like if an ant is walking on the purple graph, it doesn't matter what the x-coordinate is of that ant, it's always experiencing a slope of some positive constant, which means that the value of the second derivative function is pretty boring. It's just a horizontal line, which is just a positive constant. Its value is always that positive constant. Yeah. Yeah. Well, acceleration, time's not constant, acceleration's constant. Yeah. Okay, so does that make sense? I mean, kind of? Sort of, kind of, maybe. Does that make sense? Okay.
How is time not constant? I'm so confused.
What's that?
How is time not a constant?
Well, if time, what do you mean? Why would it be a constant? Time's a variable. I mean, time always changes. The rate at which it changes, you're saying, is constant?
Yeah.
Okay.
No, but isn't there a thing where, like, if you went, like, into outer space, like, you would age at a different rate, like, someone on Earth?
True.
Like, exactly, so therefore it doesn't increase constantly at all places in the universe.
Well, okay. I would debate that. I would debate that, but
Let's debate it.
Yeah, let's actually.
no, let's not debate that. Let's not debate that. So why don't you guys go try one of these for me, please? Go to the boards and try one.